Okay, hello. So welcome to the lab practical for computational chemistry for experimentalists, lab number 10, working on transition metal chemistry. I'm going to show you how to build the geometry of a nickel complex and how to find the lowest energy spin state. So we're going to start with the nickel hexaquo plus 2 complex. So I've got a remote desktop connection and I've got Gauss view up and running with all the environment variables set so I can run things the way I need. Just to show you, I've got a spreadsheet showing the total energies and the unpaired electrons. So I'm going to start out with building this nickel hexaquo complex. I'm going to make a new molecule, go to my periodic table tool. I'm going to get nickel, and there's an option for an octahedral coordination. So that's what I want to use. Now I'm going to add my 6 water molecules. I'm going to take these hydrogen handles and replace each of them with an oxygen. Control Z lets me undo if I need. Now these are OH groups. I have to turn them into water, so I use the add valence tool to add a proton to each of these. There's that. Now this isn't a great geometry. I'm going to use the clean tool. I'll probably use it again and again to get something that's a more reasonable geometry. Now if you look at this geometry, it doesn't actually have octahedral symmetry because the hydrogens on the water molecules are sticking off in all directions. This is what would really happen if we were in solution, except these geometries would be pretty well averaged, so the average geometry would be a high symmetry geometry. Now, I'm not going to do geometry optimizations. You know how to do that. I'm going to show you something new and interesting, which is if we have just this geometry, what are the energies of the different spin states, and how do those energies change if I do stability analysis? So I'm going to start out by preparing a calculation. This is going to be the plus 2 complex, so I need to change the charge to 2. I'm going to start with the triplet state, 2 unpaired electrons. For our purposes, I'm going to do Hartree-Fock theory calculations, and I'm going to use this Los Alamos double zeta basis set. This is usually a pretty good choice for modeling transition metals. Save a file, triplet state, and run the calculation. Okay. So I get a result. I can open my checkpoint file. Look at the summary. There's my total energy in Hartree atomic units, so I can paste that into my spreadsheet. We'll talk about that later. This is my high spin state, total energy. Okay. I can also look at my surfaces. I'm going to look at the spin density, just the density of unpaired electrons, up arrow, spin up minus spin down electron densities. So where are my unpaired electrons? I have 2 unpaired electrons. They're mostly localized to the metal, and then I have a little bit of complementary spin density on the ligands. Go to a higher density contour. My unpaired electrons are localized on the metal, and I have a pretty symmetric looking spin density. Now I'm going to do the same calculation at the same geometry, but I'm going to look at the spin singlet state. Now here I'm going to add some extra keywords to accelerate the self-consistent field convergence. So here my calculation starts running. Takes a little while. Okay. Now here there's not going to be any spin density because it's a closed shell system. I look at my results. Okay, there's my total energy. My total energy for the low spin state is substantially less negative than that for the high spin state, which kind of makes sense, but something else interesting will happen. So here's what I'm going to do. Now I'm going to show you how to do a stability analysis calculation. So this is going to be a different FAL, and I'm going to say what happens if I break spin symmetry and I allow to have, even though it's a closed shell system with the same number of spin up and spin down electrons, what happens if I allow the spin up and spin down electrons to occupy different sites, just the way that I had to do for dissociating H2. To do this, I'm going to add a couple more keywords. First is no sim. So don't use symmetry. Allow the wave function to have a lower symmetry than the rest of the system. And I'm going to do stable equals opt. This is a nice property of the Gaussian code that you can check if your wave function is stable with respect to perturbations. If it's not, you can re-optimize a lower symmetry wave function. So I'm going to save a new input file. O run stable. Submit this job. Now the calculation runs. I start doing what says a correlated calculation, and I do have an RHF to UHF instability. So I break symmetry, I have different densities for spin up and spin down electrons, and I allow the wave function to, or I try and re-optimize this new symmetry broken wave function. It takes a little while. It's taking a while to do these calculations. It's tough to converge the self-consistent field equations when you're doing this. So you might need to restart these calculations a couple different times. Maybe you use a small basis set, converge it, and then use that as a guess for a large basis set calculation. We can talk about how to do that. But this is a thing that we can do. We can just peek at this file. Doesn't seem to be printing those. Okay. Should have added an extra print flag here. Okay, so now we have an even lower energy. I'm going to, oops. Let's check that it's stable again. Open my checkpoint file again. Look at my summary. A substantially lower energy. I'm just going to put here what's my high spin to low spin gap? Before I did the stability analysis, my gap between high spin and low spin states was 338 kilojoules per mole. After I do that, it goes down to 118, so a pretty substantial difference. We're still predicting in this case that the complex is a high spin complex, but the difference between high spin and low spin states is a lot smaller than we would have expected. Now, how do we get that to happen? Well, let's take a look at our spin density. Normally, a spin singlet state has the same number of spin up and spin down electrons, so you wouldn't expect to have any spin density. But this is what symmetry breaking means. Symmetry breaking means we've broken spin symmetry, and now we have some spin up electrons in blue and some spin down electrons in green. We go to a higher surface. Look at that. We've broken spin symmetry. We've got a spin up electron in this d orbital and a spin down electron in this d orbital. Just to compare side by side, Here's the high spin complex that we looked at before. We're going to remake this spin density cube here. Use the same density cutoff to look at a surface. Okay, and here's what we see. In our high spin complex with 2 unpaired electrons, we have 2 unpaired electrons localized pretty symmetrically in that iron. We look at our low spin complex with symmetry breaking. We have spin up electron in this d orbital, spin down electron in this combination of d orbitals. So we have some broken symmetry here. Doesn't match what we have here. This substantially lowers the energy for the same reasons we talked about before. If you're looking at total energies or energy differences of transition metal complexes, you probably want to do these spin symmetry broken calculations. Later, you're going to do a mixed valence complex, so you're going to see how this spin symmetry breaking can lead to good things and bad things and complicated things. It becomes a complicated issue. The take-home message that I really want you to take back is that high spin complexes are easy. Low spin complexes, you might need to be a little more careful. Anything that's mixed valence, you need to be especially careful. So, hopefully that gives you an idea about transition metals, spin symmetry breaking. We've just started to touch on issues of transition metals. We haven't talked at all about relativity. We haven't talked about spin-orbit coupling. We haven't talked about all these other things that are going to turn out to be important if you want to look at transition metal catalysis. But this is enough to get you started. All right, I hope you enjoy. Thanks.